Okay, this video we're going to talk about transformers and power transmission. So we've probably all seen these high voltage transmission lines that we use for transmitting electrical power from generating stations to our homes. Now they're at high voltage. We often see danger high voltage signs around them. So the question is, why do we transmit it at such high voltages? Our houses use pretty much just 240 volts. Big electronic appliances like your stove will have a 240 volt plug. So why don't we transmit at 240 volts rather than such a higher voltage? Well, it has to do with the resistance of the wires themselves. If we transmit current through those wires, then they have to overcome the resistance of the wire itself, and we lose power during transmission. So let's do some simple calculations. Suppose we have a power generating station that generates 120 kilowatts of power, and we're transmitting it over wires which have a pretty low resistance of 0.40 ohms. But even still, it's not zero, so when we transmit this electrical power over these wires, we're going to lose some power. So the first thing we want to do is figure out what is the current that's being transmitted through these wires. So again, we can divide the power by the voltage, and if we're transmitting it first at, let's say, 240 volts, the voltage that we said we would want in our house. So we're going to take the 120,000 watts and transmit it at 240 volts. That works out to be a current of 500 amps. So we have 500 amps of electricity running through these wires. So how much power do we lose? Well, if we have current running through a resistor, we take the square of the current and multiply by the resistance. And what we end up with is we're going to lose 100,000 watts of power. Almost all of the electrical power is used up just overcoming the resistance of the wires. However, if we transmit at a higher voltage, let's say 24,000 volts, now what we see is that we transmit at a much lower current, because we're going to divide that electrical power by a higher voltage, giving us only 5 amps of current. And if we transmit a lower current over that resistance, we get less electrical power lost. So 5 squared times 0.40 ohms, that works out to be only 10 watts of lost power. So we transmit electricity at high voltage and low current to reduce the amount of power we lose during transmission. Okay? So we have less current flowing through the wire, but the current that is flowing through the wire is carrying more electrical energy. Remember, voltage is the joules, the energy per charge. So each charge itself has more electrical energy, but there's fewer charges flowing through the wire. So that's why we transmit at high voltage. But that means that we need some method of converting the current that comes into our house from this high voltage to the lower voltage that we need. And that's where this idea of a transformer comes in. Now, it's not this type of transformer. It's this type of transformer. If you look around your neighborhood, you'll see these gray garbage type looking things, and they're actually transformers. So the wires themselves are carrying electrical voltage, usually around 24,000 volts or so, and we want to step down that voltage down to 240 volts. And that's what this transformer does. You'll also see transformers like these, electrical substations around town. So basically the high voltage wires, which are up in the hundreds of thousands of volts, come into a substation and get dropped down one step. So what is a transformer itself? Well, a transformer is basically an iron core with two solenoids, so two sets of windings. We call this side the primary coil or the primary windings, and then this side the secondary coil or the secondary windings. So what we have is current coming into this coil at one current and one voltage. And because our electrical generating stations create alternating current, the current is vibrating back and forth. So that creates a magnetic field in this coil of wire. And that magnetic field is constantly changing direction because of the alternating current. Okay, so here is our magnetic field, and it's constantly changing direction. Now, as that magnetic field is expanding and collapsing, it's passing over this secondary coil. And we know from Faraday's experiments that when we have a changing magnetic flux over a coil of wire, we can induce a current. And because this coil of wire has fewer coils, you'll see the primary coil here, the primary turns, there's fewer windings than over here, it gets a different amount of current. So a different current and a different voltage due to the different number of coils. That's a basic transformer. So we have current coming in one end at one voltage, creating a changing magnetic flux, and that changing magnetic flux induces a different current and a different voltage in the secondary coils. And that's a basic transformer. So what we have is our generating station, whether it's a coal-fired or nuclear-fired or a hydroelectric dam, it's generating electrical power. Usually we'll have a transformer substation at the generator which steps up the voltage for transmission. Then we have electrical transmission lines which carry the electricity long distance. Then another neighborhood transformer, those little substations that I showed earlier, stepping down the voltage. It goes on to our telephone poles for transmitting around our community at a somewhat lower voltage. Then another one of those garbage can type transformers which steps it down again before it comes into the house. Okay, let's actually take a look at a question involving transformers. So what we have here is a transformer, and remember a transformer is basically two coils of wire. So we have something called the primary coil and something called the secondary coil. And the primary coil, we're told, has 840 windings or turns, and the secondary only has 56. And we know that the primary is connected to 110 volts, so basically it's connected to our outlet on our wall, and it's providing 0.3 amps. So we're asked to find what is the voltage over here. Notice the different number of turns in each of the primary and the secondary. Now we have a very simple relationship between voltage, current, and the number of turns. Basically, if we take the ratio of the voltages and the ratio of the number of windings, we find that they're equal. And for the current, it's opposite. It's primary divided by secondary. Because remember, if the voltage goes up, the current will go down. So that's why this has to be inverted. So what we know here is that we have voltage and the number of turns. So if we're looking for the voltage in the secondary, all we have to do is look at the ratio of these two sides of the transformer. And we can find that what we have is a decrease in voltage from this side to this side. So we're going from 110 volts down to 7.3 volts. Very often there'll be a part B to this question which might say, is this a step up or a step down transformer? And again, what they're referring to there is the voltage. Is the voltage going up or is it going down? In this case, because it's going down, we know that this is a step down transformer. Okay, very easy part B. Notice that we could also find the current if we wanted. What we would find is the current probably increases. I'll leave that calculation to you. I think it's fairly straightforward. There's lots of good questions, sample questions in the textbook on transformers. I think you'll find them relatively easy, pretty easy points to get on a test. If you have any questions though, as always, come and track me down in class.